Hi everyone, this is Sridhar Chintala, Assistant Professor of Physics, ABV Government Degree College, Janagaon. So, so far I am making video lectures on the unit called Statistical Mechanics, which is of BSc Physics, second semester, Thermal Physics, and Unit 4, the Statistical Mechanics. So far we discussed about the statistical mechanics, the postulates of statistical mechanics and basic definitions, phase space and concept of ensemble, the different types of concepts of ensembles. And then we discussed about what is called the Maxwell-Boltzmann statistics, and we also discussed the Bose-Einstein statistics. And in the today's class, we are going to discuss about the Fermi Dirac statistics. So in this video lecture, I would like to discuss the Fermi Dirac statistics. So in order to discuss Fermi Dirac statistics, we have to have an idea about the quantum statistics. So how the statistics is divided into classical and quantum statistics, and what is called the Fermi Dirac statistics, and what are the conditions to be satisfied by a system of particles under consideration for the Fermi Dirac statistics, and what is the expression for the occupation index, and then the applications of Fermi Dirac statistics to the white dwarfs, neutron stars, pulsars, and black holes, and as well as the comparison of the three distribution formula or distribution laws. So we'll discuss these topics one by one. So this is the Fermi Dirac statistics from BSc Physics second semester, the paper titled as Thermal Physics, and Unit 4 titled as Statistical Mechanics. So as far as the statistical mechanics is concerned, it is classified into two mechanics. One is classical mechanics and the second one is quantum statistics, classical statistics and quantum statistics. So the statistics, the meaning of the statistics is mainly it is dealing with the large number of combinations or large number of molecules or atoms or particles. So if you use the classical statistics, that means if we define the system using classical mechanics, so that is uh, defined as the classical statistics. So the system which satisfies the Maxwell-Boltzmann law or Maxwell-Boltzmann statistics comes under the classical statistics. So in the classical statistics, the particles or molecules are identical but distinguishable. Whereas the quantum statistics, the particles are identical but indistinguishable. And in turn, the quantum statistics is divided into or classified into two, where the spin quantum number comes into the picture. So if the particles are having integral multiples of h by 2 pi, the spin is integral multiple of h by 2 pi, then they are called as the bosons, and the concerned statistics is called the Bose-Einstein statistics. The examples of bosons are photons and the helium 4 atom. And whereas if the particles are having half odd integral multiples of spin or of odd integral multiple spins, then the particles are called fermions, and the statistics, the related statistics is called Fermi Dirac statistics. So in this class, we are going to discuss the Fermi Dirac statistics in detail. So Fermi Dirac distribution law. So in the Maxwell-Boltzmann statistics and the Bose-Einstein statistics, there is no restriction on the occupancy of particles in any energy state. So as far as the Maxwell-Boltzmann statistics and Bose-Einstein statistics is concerned, there is no restriction on the occupancy of particles in any energy state. But whereas in the Fermi-Dirac statistics, applicable to particles like electrons and obeying the Pauli's exclusion principle, the Pauli's exclusion principle is saying that no two electrons in an atom have same energy state. So only one particle can occupy a single energy state. So unlike MB statistics and BE statistics, in the case of Fermi-Dirac statistics, only one particle should occupy a given single energy state. So whereas in the case of Bose-Einstein statistics, one cell or one energy state may have total number of the particles, or it may have zero particles. That means it may even empty also. But whereas in the case of Fermi-Dirac statistics, the one energy state should contain only one particle obeying the Pauli's exclusion principle. According to Pauli's exclusion principle, no two electrons in an atom have same energy states. And the Fermi-Dirac statistics is applicable to particles of half-odd integral spins, that is h cut by 2, 3h cut by 2, and 5h cut by 2. The particles like electron, proton, and neutron, where h cut is equals to h by 2 pi, and h is the Planck's constant, which is given by 6.62 into 10 to the power of minus 34 joule second. So this is the Fermi-Dirac statistics. So in order to derive the Fermi-Dirac distribution law, let us consider a system of consisting of n independent identical particles. And such a system can be described by means of a complete set of eigenfunctions that are antisymmetric under the exchange of any pair of particle coordinates. So whereas in the case of Bose-Einstein distribution law, the system is symmetric by the exchange of any pair of particle coordinates. Since only one particle can occupy each energy state, so exchange of the two particle, any pair of particle coordinates gives out to be a new state. So that means the system is antisymmetric under an exchange of any pair of particles coordinates. And the energy levels of these particles are discrete, and the number of particles in each cell or in each of the GI subcells of the ith cell is either 0 or 1. It may contain 0 or it may contain 1. Whereas in the case of Bose-Einstein statistics, we may have either 0 or total Ni particles in a given energy state. But whereas in the case of Fermi-Dirac statistics, a state should contain only one particle. Either it is one particle or it is no particle. That means either it is 0 or equal to 1. And the conditions in the Fermi-Dirac statistics are: the particles are indistinguishable from each other, so that there is no distinction between two different ways in which Ni particles can be chosen. This is first condition, the condition number 1. And each cell or sub-level may contain either 0 particles or Ni particles. Okay. Obviously, Gi must be greater than or equal to Ni. So that means the energy levels must be greater than the number of particles. And the sum of energies of all the particles in different groups taken together constitutes the total energy of the system. And here Ni particles can be distributed in Gi state by a number of ways, and that number of ways can be calculated or obtained as follows. So we'll discuss that in the next slide. So this figure gives the picture of the cells and particles. So whereas the black dots represents the partitions, and those partitions gives out to be cells, and we may have the particles in the given cells, which are indicated by Gi. So the Gi subcells are constituted by Gi minus 1 partitions, which are represented by Gi minus 1 black balls. So we easily find that the first particle can be put in any one of the ith cell in Gi ways. Since there are Gi energy levels, so we can put one particle in Gi minus 1 partitions by Gi ways. So according to Pauli's exclusion principle, no more particle can be assigned to that field state. So the second particle can be put in the next Gi minus 1 subcells in Gi minus 1 ways, and so on and so forth. So for example, there are 10 cells. So if you want to put one particle in the cells, so we can put in 10 ways. So we may put the first particle in first one, second, a third, and fourth, and so on and so forth up to 10. So that means we may put the first particle in 10 different ways. Whereas if you consider the second particle, already first state is filled, so we have only 9 ways. So that means the second particle can be put in the next Gi minus 1 subcells in Gi minus ways, and so on. And if you consider the third particle, it will have Gi minus 2 ways. So like that, so the number of ways in which Ni particles can be assigned to Gi states is Gi into Gi minus 1 into Gi minus 2 into Gi minus Ni minus 1 is equals to Gi factorial by Gi minus Ni factorial. So this is the way in which we can arrange, or we can distribute Ni particles in Gi states. So where the Ni particles can be chosen among themselves in Ni ways, so that we have to subtract those permutations from the total number of permutations. So we are having Gi partitions, Gi factorial by Gi minus Ni factorial. So this is the number of ways in which Ni particles can be assigned to Gi states. So further, since the particles are indistinguishable, it is not possible to detect any difference when Ni particles are reshuffled among themselves. So this is possible in Ni different ways, so that we are taking the what is called, we are subtracting those Ni from Gi. So thus the total number of different and distinguishable ways is Gi factorial by Ni factorial into Gi minus Ni factorial. So the above expression gives the total number of ways in which Ni similar particles can be fixed in available Gi cells with only one particle in one box. And the total number of ways of getting the distribution N1, N2, N3, and so on and so forth among the various energy levels E1, E2, E3, and so on and so forth respectively can be obtained by multiplying the various terms of the same type. Thus the thermodynamic probability of Ft distribution is given by W is equals to pi I Gi factorial divided by Ni factorial into Gi minus Ni factorial. So actually this term gives the probability of distribution of Ni particles in Gi levels for one state. So likewise we are having from E1 to En states. So we can expand the total distribution and we can obtain the thermodynamic probability of Ft distribution as W is equals to pi I Gi factorial by Ni factorial into Gi minus Ni factorial, and taking the natural logarithm on both sides, this is log W is equals to, so when you are applying log, this product will be replaced by sum. So since log A by B is equals to log A plus B, so like that we can write the summation, the product by summation. So summation log Gi factorial minus log Ni factorial minus log Gi minus Ni factorial. And again, applying the Stirling approximation, we have log W is equals to summation Gi minus log Gi minus Gi minus Ni log Ni minus Ni, and here this minus into minus becomes plus Ni, and minus Gi minus Ni into log Gi minus Ni minus Gi minus Ni, and here we are having already minus sign, so it is minus into minus plus, and here we are having minus Gi and plus Gi, plus Ni and minus Ni, so all these terms will be cancelled. So here we are having negative minus Gi here and plus Gi here, minus Ni here and plus Ni here. So all the terms will be cancelled, and we are left with Gi into ln Gi minus Ni into log Ni minus Gi minus Li into log Ni Gi minus Ni. Though the three terms will be left in the equation. So then the log W is equals to summation Gi log Gi minus Ni log Ni minus Gi minus Ni into log Gi minus Ni. And here Gi is not subjected to variation and Ni varies continuously. So for the most probable distribution, we have the change in the log W maximum is equals to 0. So as Gi are the energy levels, there is no variation, and Ni is the number of particles. So the number of particles only the changing variable. So that for the maximum probability, if you want to derive differentiate this equation, you will have delta log W maximum is equals to summation, and this term goes to 0 since there is no variation in Gi's. So minus Ni into log Ni, and that gives to be, I will take the annotation. So here on differentiating the equation, we have Ni into 1 by Ni, since log x is 1 by x, d by dx of log x is 1 by x, so it is 1 by Ni, so with a negative sign. And here this is log Ni into delta Ni for the second term, and for the third term it is Gi minus Ni into the differentiation of log is Gi minus Ni. So this and this will be cancelled, this and this will be cancelled, and this is minus 1 and this is plus 1, these two are cancelled, and we left with log Ni delta Ni plus log Gi minus Ni into delta Ni. So these are the two terms left in the equation. And again we are taking the first conditions, that is the total number of particles is equals to constant and the total energy of the system is equals to constant. And if you take the variation in the total number, that is summation delta Ni is equals to 0, and the variation in the total energy is sum of summation Ei delta Ni is equals to 0. And again we are multiplying this with some constant alpha and multiplying this with some constant beta and subtracting these two from this equation, and we'll have the equation as, so multiplying this equation 6.37 by minus alpha and equation 6.38 by minus beta and adding to the equations, we have summation minus log Ni plus log Gi minus Ni minus alpha minus beta Ei into delta Ni is equals to 0. And as the variations delta Ni are independent of each other, we get this term goes to 0. So log Gi minus Ni by Ni, these two terms, minus alpha minus beta Ei is equals to 0. And if you apply the anti-logarithm, we'll have, here again I have to take the annotation. So here this is Gi minus Ni divided by Ni is equals to e power minus alpha into e power minus beta ei. And if you want to write for ni, this will be is equals to ni into the whole term e power minus alpha into minus beta ei, and this ni comes this side, so becomes plus ni is equals to gi. So on taking ni as common, we are left with e power minus alpha into minus e power minus beta I plus 1 into n1, and n1 is equal to gi by, sorry, ni. So ni is equal to gi by, so this term. So on bringing these two terms this side, these two becomes plus. So e power alpha into e power plus beta ei. So this is ni is equals to gi by e power alpha into e power minus beta ei plus 1. So this is called the Fermi Dirac distribution law for the distribution of ni particles in given gi subcells by obeying the Pauli's exclusion principle, that is no two electrons will have same energy states. That means one energy state will be occupied by only one particle. So the equation 6.39 is known as the Fermi Dirac distribution law. So here we can summarize, we can write the equation in terms of temperature for the system consisting of fermions in statistical equilibrium. One can show that beta is equal to 1 by kT and alpha is equal to minus EF by kT, where EF is called the Fermi energy. And we can write that Ni is equal to Gi by e power alpha into e power minus e power Ei by kT, and this will be e power Ei minus Ef by kT, where this alpha is equal to e power Ef by kT minus Ef by kT. So this is the Fermi Dirac distribution law in terms of temperature. And with this we can define what is called the definition of Fermi energy. The Fermi energy is defined as the at absolute zero of temperature T is equal to 0 Kelvin, the maximum kinetic energy that a free electron can have is called the Fermi energy, EF. That means we have to substitute T is equal to 0 in this equation. So if you substitute 0 in that equation, you will get Ni is equal to Gi by e power Ei minus Ef by kT plus 1. So if you substitute T is equal to 0, you substitute T is equal to 0, what you get is e power infinity, and that is equals to that will be equal to what is called 0, e power infinity is equal to 0. So Ni is equals to Gi, and if you take the ratio Ni by Gi, that will be equal to 1. That means at T is equals to 0, we can have Ni by Gi, the ratio is equals to 1. That is called the occupation index. That means the occupation index is 1, means that is fully filled. So this graph is showing the variation of the occupation index with the energy. So at T is equals to 0, the energy is EF and the ratio is Ni by Gi is equals to 1. And if you change the temperature, so at low temperatures, the occupation index decreases, and at high temperatures also the occupation index is decreasing, but in a different manner. So at low temperatures, initially it is showing this behavior, and for high temperatures it is showing this behavior. So that is called the Fermi Dirac distribution, and this is explanation of the graph. So for T is equal to 0, and if the energy is less than Fermi energy, all the energy states are fully occupied, and that is Ni is equals to Gi. And all the states with Ei greater than Ef are empty, that is Ni is equals to 0. For higher temperatures, some particles also occupy higher energy states greater than EF, that is EI is greater than EF for some particles. So the curves indicate that only those fermions with energies close to EF can move into unoccupied higher energy states. So this is the explanation of the that graph, and the comparison of three distribution laws. So we can write the three distribution laws at a time. So with one equation. So this is the Fermi, the distribution function for Maxwell-Boltzmann distribution, and this is the distribution function for Bose-Einstein, and this is the distribution function for the Fermi Dirac. So in the Maxwell-Boltzmann distribution function, we have e power alpha plus ei by kt, and in the Bose-Einstein case we are having -1, and we are having the in the Fermi Dirac case it is +1. So we can summarize all these by some equation, one equation called f of ei is equal to 1 by exponential of alpha plus beta ei plus delta, and the quantity f of ei is ni by gi is called the occupation index of a state of energy ei, and this is the probability of occupation of a single state at energy ei, and delta is equals to +1 for Fermi Dirac, and it is 0 for MB, and it is -1 for BE statistics. And f of ei is referred to as the occupation probability or the distribution function. So this is how we can express the three distribution laws with one equation, which is given by f of ei is equals to 1 by exponential of alpha plus beta ei plus delta, where delta is equal to 0 for MB case, and it is -1 for the uh, BE case, and +1 for the Fermi Dirac case. So this is how we can compare the three distribution laws: Maxwell-Boltzmann, Fermi Dirac, and Bose-Einstein. So MB, FD, and Bose-Einstein. So as far as the particles are concerned, in the case of Maxwell-Boltzmann, we have the particles are the distinguishable, and only particles are taken into consideration. And in the case of Fermi Dirac, particles are indistinguishable and quantum states are taken into consideration. Here particles are taken into consideration, here quantum states are taken into consideration. And in the case of Bose-Einstein, the indistinguishable particles and quantum states are taken into consideration. And in the case of classical, there are no restrictions on the number of particles in a given state. And in the case of the Fermi Dirac, only one particle may be given to given quantum state. And in the case of Bose-Einstein, there is no restriction on the number of particles in a given state. Maxwell-Boltzmann law applied to ideal gas molecules, and Fermi Dirac is applicable to the electrons and elementary particles, and the Bose-Einstein is applicable to photons and symmetrical particles. As far as the internal energy is concerned, in the case of Maxwell-Boltzmann equation or the distribution, internal energy of ideal gas molecule at absolute zero is taken as 0. And in the case of Fermi Dirac, even at absolute zero, the energy is not 0. And the energy at absolute zero is taken to be 0 in the case of Bose-Einstein statistics. And in the case of Bose-Einstein, in the case of Maxwell-Boltzmann statistics, at higher temperatures, BE and FT distributions approach to Maxwell-Boltzmann distribution. And at higher temperature, Fermi-Dirac distribution approaches to Maxwell-Boltzmann distribution. So the same one. And the most probable distribution is given by f of ei is equals to 1 by exponential of alpha plus beta ei. And in the case of Fermi-Dirac, it is +1. And in the case of Bose-Einstein, it is -1. So it can interpret many observable phenomena such as temperature, pressure, energy, and it could give an explanation for specific heat of variation that is from the Fermi-Dirac statistics. And we can explain the phenomena of blackbody radiation from Bose-Einstein statistics. So that means the Bose-Einstein statistics is applicable to the photons. So we derived the Planck's radiation formula, and this Fermi-Dirac statistics is applicable to the electron gas, and we can explain the specific heat variation of the solids using the Fermi-Dirac statistics. And the classical phenomena such as temperature, pressure, and energy can be explained using the Maxwell-Boltzmann statistics. So it is applicable to the ideal gas equation, that is PV is equals to RT, and Fermi-Dirac gas has higher pressure than that given by PV is equals to RT, and BE gas has a lesser pressure than that of the pressure given by ideal gas equation. So these are the comparisons of three distribution laws. And application of the Fermi Dirac distribution in order to find out the Fermi energy of a electron gas. So in case of particles following Fermi Dirac statistics in thermal equilibrium at absolute zero, the energy levels from 0 to a certain value of EF occupied by the particles, and other energy levels above EF are vacant. So the energy is known as Fermi energy. So in the case of particles following the Fermi Dirac statistics in thermal equilibrium at absolute zero, the energy levels from 0 to a certain value of EF, those are occupied by the particles, and the above EF are vacant. So the energy is known as the Fermi energy. So according to distribution law, the number of particles having the energy between E and E plus dE is given by N of E into dE is equals to G of E into F of E into dE. It is given by G of E into dE divided by E power alpha plus B EI plus 1, where this is F of E is equals to E power alpha BI plus 1. That is the Fermi Dirac distribution function. And G of E into dE is equals to 2 into 4 pi P square V dP by H cube, where this 2 term, the factor 2 is introduced due to the two values of electron spins. It can have +1 and -1. So it is having two spins. So that is the reason we are having this multiplication factor in the distribution of energies. That is G of E into dE, that is the energy levels. So substituting equation 2 in equation 1, we are having N of E into dE is equal to 8 pi P square V dP by H cube into F of E. And the total number of electrons in the system is given by N is equal to integral 0 to infinity N of E dE is equal to integral 0 to infinity 8 pi P square dPV divided by H cube into F of E. And at absolute zero, F of E is equals to 1 for E less than EF, and it is equals to 0 for E greater than EF. So that means the energy levels which are below the Fermi level are completely filled. So the occupation index is equals to 1, and the energy levels which are above the Fermi level are unoccupied. So the occupation index is equals to 0. So the total number of particles N is equals to integral 0 to infinity 8 pi P square dPV by H cube into F of E is equals to, so this F of E is equals to 1 for energy levels E is equals to EF. So we are integrating this P square into integral P square is P cube by 3. So capital N is equals to 8 pi V by H cube into P cube by 3 from E to EF. So we know that P square is equals to 2me, and m is the mass of electron, and where when E is equals to 0, P is equals to 0, and E is equals to EF. So P is equals to under root 2mEF. So that means we can substitute in place of P, we can substitute root 2mEF in the place of P. So on substituting that, we have capital N is equals to 8 pi V by H cube into 2mEF to the power of 3 by 2. Since here we are having a root and this is having a third power, so it is 3 by 2 by 3 from E to EF. So when you substitute EF, it will be EF, and when you substitute 0, this term, whole term goes to 0. So that means we are left with only one term. So capital N is equal to 8 pi V by H cube into 2m e to the EF to the power of 3 by 2 by 3. And this implies, if you write for EF to the power of 3 by 2, this H cube goes this side and 3 goes this side. So 3H cube into N divided by 8 pi V into 2m to the power of 3 by 2. And this will be equal to 3H cube by small n, so 3H cube into small n by 8 pi into 2m to the power of 3 by 2. Since N by capital V is equal to small n, the number of molecules per unit volume, so where n is equal to capital N by capital V. So hence we have the expression for EF as h square by 2m into 3n by 8 pi V to the power of 2 by 3. So this is the Fermi energy of electron gas, and this will be very useful in calculating the mass of the white dwarfs and the mass of the what are called the neutron stars. So how stars can support themselves against gravity, the stellar evolution. So in the stellar evolution, we are going to discuss about the white dwarfs. So stellar evolution is the process by which a star undergoes sequence of radical changes during its lifetime. So depending upon the mass of the star, the lifetime ranges from 1 year to a few million years, a few million years to few trillions of years. So that depends upon the mass of the star, considerably more than the age of the universe. So a star in its final phase of stellar evolution is called the white dwarf. So if the thermonuclear fuel of a star has been exhausted, the star contracted gravitationally until its atoms collapsed into nuclei and electrons packed closely together. So white dwarf stars have masses comparable to that of the sun. So the densities of white dwarfs exceedingly high, of the order of the 10 to the power of 7 to 10 to the power of 10 kg per meter cube. So atoms under the densities prevalent in white dwarfs are entirely ionized into nuclei and free electrons, and the electron gas is a degenerate gas. So in the case of white dwarfs, the what is called the thermonuclear fuel of the star is totally exhausted, and they are ionized into nuclei and free electrons gas. So that means nuclei are separated and electrons are separated. So that constitutes an electron gas, which is a degenerate gas. And this degenerate gas exerts pressure, and due to that pressure, these stars contracts to white dwarfs. So in the interior of a white dwarf star, the electron gas is degenerate. The temperature is much less than the Fermi energy, and the Fermi energy of an electron gas of volume V at a concentration of 10 to the power of 36 meter cube per meter cube electrons is given by the equation EF is equal to h square by 2m into 3n to the 3n by 8 pi to the power of 2 by 3. The equation we already discussed one. So the Fermi energy, the Fermi temperature EF by K of the electrons is of the order of 3 into 10 to the power of 9 kelvins. So the electrons in the interior of a white dwarf are highly degenerate because the thermal energy is much lower than the Fermi energy. So in its final stages of evolution, the star consumes its lost nuclear energy resources, and the nuclear reactions come to an end. So the nuclei cool down and come together under the influence of gravitation. The enormous 0-point pressure exerted by the electron gas is counteracted by the gravitational attraction. So thus the size of the white dwarf is determined by a balance between the inward gravitational pull of its atomic nuclei and the pressure of its degenerate electron gas. And no white dwarf star can have a mass larger than m is equals to 1.4 into mass of the sun, and this mass is known as this Chandrasekhar limit. So Chandrasekhar has given a limit for a star to become a white dwarf. If the mass of the star is larger than 1.4 times of the sun, it becomes a white dwarf. So that limit is called the Chandrasekhar limit. So a limit which mandates that no white dwarf can be more massive than 1.4 solar masses. Any degenerate object more massive must inevitably collapse into a neutron star. So this is the Chandrasekhar Venkatraman. So gas and radiation pressure supports stars in which thermonuclear reactions occur. Pressure of a degenerate electron gas at high density supports the objects with no fusion, dead stars called white dwarfs, and the cores of giant planets Jupiter, Saturn, etc. So the pressure of a degenerate neutron gas at high density support neutron stars. So the relativistic and non-relativistic expression for electron degeneracy pressure are equal at about Ne is equal to 10 to the power of 36 per meter cube, about that of a core of a 0.3 m of white dwarfs. So as long as the star is not too massive, the Fermi pressure prevents it from collapsing under gravity and becoming a black hole. And this is the picture which gives the definitions of white dwarfs, black holes, and neutron stars. So if the mass is less than 1.4 solar masses, so that is a white dwarf, electrons run out of room to move around, electrons prevent further collapse. The protons and neutrons still free to move around. So stronger gravity, more compact. And if the mass is greater than 1.4 solar masses, but mass is less than 3 solar masses, so it becomes a neutron star. So electrons plus proton combine to form the neutrons, and neutrons run out of room to move around. Neutrons prevent further collapse, much smaller. And if the mass is greater than 3 solar masses, it becomes a black hole, and gravity wins, nothing prevents collapse. So this is how the star evolution is taking place. And then we have the neutron star. The neutron star is nothing but the a gravity stopped by neutron degeneracy is left behind the supernova explosion and is called a neutron star. So neutron stars will have a mass m greater than 1.4 times of m sun, that is the mass of the sun, and in the form of a ball of neutrons about 15 to 20 kilometers across. So density is far beyond that of anything familiar, like taking two of our suns and squeezing them into one mountain-sized volume. So neutron stars should be so tiny that no matter what their temperature, it is doubtful that they could ever emit enough visible light to ever be seen. So a neutron star consisting of a super dense mass mainly of neutrons, and then a pulsar. So pulsar is a neutron star that is rotating rapidly. So neutron star is a star which is having a mass greater than 1.4 times of this solar mass, and a pulsar is a rotating neutron star. So why do neutron stars appear to us as pulsars? So all stars spin, any spinning object that pulls its mass in closer will start to spin faster. So conservation of angular momentum. So the collapse of material inward should cause neutron star to be rotating very fast. So the faster rotation should also cause neutron stars to have extremely powerful magnetic fields. The passing particles will be directed around the neutron star towards the magnetic poles. So that is the reason the magnetic fields will cause the particles to move in swirling pattern that should result in the emission of what is called the synchrotron radiation. So synchrotron is a large device that uses magnets to make particles to move in spiraling paths, and those particles emit radiation. So for the magnetic fields and the speeds involved, the synchrotron radiation should be radio waves. And if the Earth happens to be in the right direction, we will see a flash of radio waves once with each rotation of the neutron star, and the neutron star appears as a pulsar. And then we are having the concept called the black hole. The limit for white dwarfs is 1.4 solar masses, the Chandrasekhar limit. And there is a mass limit for the neutron star about 2.5 solar masses. What happened? A neutron star to have a mass of 2.5 solar masses or more. So a neutron star is made of neutrons and they are already squeezed together to the limit that allowed by a neutron degeneracy. So possibly a neutron star can explosively contract into an even denser, and that name is called a quark star. So but at a mass of about 2.5 solar masses, we get an entirely new type of object called the black hole. So the black hole can be viewed as a space around this dense mass and not due to the new composition. So Schwarzschild found that for any given mass, there was a certain radius where time was compressed down to zero, while the spatial dimensions stretched to infinity. So this radius is now known as the Schwarzschild radius is very small, about 3 kilometers for a star with the mass of our sun. So a star whose radius is smaller than its Schwarzschild radius is known as a black hole. So no light can escape from the surface of a black hole. So these are the applications of the Fermi Dirac statistics. So in order to derive the Fermi energy of a degenerate electron gas, and on the basis of degenerate electron gas, we can define what is called a white dwarf and what is called a neutron star, and what is a pulsar and what is a black hole finally. So far in this video lecture, we have discussed about what is called the statistical mechanics and how that statistical mechanics is divided into classical and quantum, and how the quantum mechanics further divided into Bose-Einstein and Fermi-Dirac statistics, and what is the system what we consider under Fermi-Dirac distribution law, and what are the conditions to be satisfied by that system in order to derive the Fermi-Dirac distribution law, and what is Fermi-Dirac distribution law, and what is called the Fermi energy, and how the particles are occupied depending upon the energy of the states, so fully filled and unoccupied, and the applications of Fermi-Dirac statistics. So this is as far as the Fermi-Dirac distribution law and Fermi-Dirac statistics is concerned. So thank you for your patient listening. Thank you very much.